question 1, multiple choice, or do we go to question 2, which is Newton's second law? Where do we start?
Can we start with work, energy, and power? The work, energy, and power question.
Work, energy, and power. Okay, that's fine. So I guess everyone have unmuted their mics at this point, just so that we can talk. Otherwise, it's gonna be very, very useless if maybe we don't communicate, That's why I see that contact classes are way, way better because we can talk face to face. Online, everyone else can just mute their mics and it's no longer, it's no longer working. Okay, this is the work, energy, and power question. Let's see if there's another one. Okay, this is the only one. So it's question 5. All right, you can start. So the question says an object of mass 1.5 kg slides down a rough curved track and passes point A, which is 1.5 meters above the ground at a speed of 0.95 meters per second. Okay, so whenever you get a question, I always say this: the first thing you want to do is to draw a sketch. If you already have a nice enough sketch, then you can just go and write all the given data on your sketch. So let's see if everything is represented. In this case, we have an object of 1.8 kg that's there. We have 1.5 meters above for point A, that is also indicated. We have the speed at point A of 0.95 meters per second. That one is also there. So we have also when it reaches point B at the bottom of the track at a speed of 4 meters per second. So that one is also indicated for us. So that's good. Now the first question is, and I want to hear these ones from you guys. 5.1, define the term conservative force. Anyone want to take this one?
It is a force in which the work done by the force does not depend on the path taken.
Yeah, I hope everyone knows these things by now. 2 marks for every question, sometimes 2 of them. So conservative force, any example of a conservative force from someone else?
Gravity.
Yeah, FG. So these ones are independent of the path taken. So the work done by them is independent of the path taken. Doesn't matter how we travel, the work done is still going to be the same. So the definition itself should make sense. Otherwise, if you are a pro at cramming, then it doesn't have to make sense. Okay. 5.2 says name the conservative force acting on the object. So that one is straightforward. It's just gravitational force. So I'd say you write it in words. Gravitational force. Okay. 5.3 is mechanical energy conserved as the object slides from point A to point B. Choose from yes or no and give a reason. What do we say?
I feel like it's not.
Okay, the answer should be yes or no, and then a reason.
I would say no because it's moving across a rough track. Isn't gonna lose some energy when fighting against friction.
Okay, any different answer from that? Any different opinion? Okay, I take this none. Yeah, you are definitely correct. The answer is no because they did mention Remember the thing I said about highlighting? They did mention that the path is rough. So that implies to you that there is friction on that. They also indicated with this jagged lines, I guess, so you can see that the path is rough. Or you can go back to the statement and reread it again. Then you see that there's friction. Okay, so for the reason you're going to say there's a friction of force. So friction of force is present. And friction of force, we know, is a non-conservative force. So whenever there is a non-conservative force, we know that mechanical energy is not conserved. Okay, that's one of the things I hope you know. 5.4 says calculate. Yes.
I was asking, is it because if like there's friction, does that mean that the system is no longer an isolated system?
Yeah, that's true. When there's friction,
Okay.
there's external forces, which means it's no longer an isolated system. That's also true. Okay. Make sure you speak, because I might be fast thinking that maybe we are on the same track and maybe we are not. So if you have a question, don't hesitate to stop me. 5.4, calculate the gravitational potential energy of the object when it was at point A. That's fine. That looks like it's too simple. We'll go to 5.5. Using energy principles, calculate the work done by friction on the object as it slides from point A to point B. So I'll combine these two to be 7 marks, because we can do this one, but we're going to use that answer to do 5.5. So let's look at how we're going to solve that. Using energy principles. So energy principles we know is, or you can go to the formula sheet to check those, but
I have a question.
yes.
When it comes to the non-conservative forces on this, is it only friction or do we also count force moment?
Okay, let's talk about that a bit. Non-conservative. Okay, let's write examples of these. So there's friction. What else from others?
Tension.
Yeah, we also have tension. What else?
Force applied.
Yeah, obviously also applied force. And maybe the list can go on, but these are all the forces that are going to, let me just see if I can make an example. If this is friction, this is tension, this is force applied. So we have our Fg going down this way, we have our normal force. So you can see these ones are forces that can directly impact the motion of the object. If maybe the definition doesn't really make sense, these are forces that will depend on what the path you take. For example, if I go from A to B like this, the applied force, the work done by the applied force is going to depend on the change in X. For example, the work done by tension and friction the same, but the work done by Fg is not going to depend on change in X. It's going to be 0 to actually, because this is a level plane. But if I take a path like this, we can calculate the total distance from point A to point B, and the work done by friction, tension, and applied force is going to depend on this distance, the whole distance. So it's going to be larger as the distance is larger. But the work done by Fg, you'll see that it's only going to care about this height here between A and B. It doesn't care about anything else on the path, only the height from A to B. Yeah, so if maybe you happen to forget what your non-conservative forces
And
are.
then with force normal, when it doesn't, the direction of the force isn't gonna change as you move along that distance. So it doesn't count as a non-conservative force.
Okay, let's look at the normal force. That's a good question. So I'll draw the object at some 4 points here. So if we look at the normal force, this one they say is always perpendicular to the surface, right?
Yes.
And what do we know about the work done by a force that is perpendicular to the direction of motion?
Oh, it's zero, of course.
Yeah, it's always going to be zero. We can check FG. FG is not always perpendicular to the direction of motion, as we can see. So the work done by FG is not zero, but normal force, it's always going to be zero.
Okay.
Yeah. Okay. Good questions there. We can proceed. So we were on 5.5. Let's see how we can solve that one. Which equation would we use?
I'd say the work done by non-conservative force as well.
Yeah, because we have non-conservative force, which is friction, and we also see that we have a change in height. So according to the notes I gave you the other time, we can see that the easier equation to use here will be that work done by non-conservative forces. So let's do that. So the formula says work done by non-conservative forces is equal to change in potential energy plus change in kinetic energy. We can expand it as well. So we know that our work done by non-conservative forces is just going to account for all the work done by friction or tension or applied force. We only have friction, so the work done by friction is what? Is going to be the force of friction times the distance we travel multiplied by the cosine of the angle theta, and this is going to be equal to potential energy is mgh. Final, I'll use the letters given. So I'll say the final obviously is at point B minus mgh at point A plus 1/2 of mv squared at point B. That's our final, minus 1/2 of mv squared at point A. That's our initial. Okay.
Wait, aren't we gonna keep the other side the same? Since we're not looking for friction, we're mainly looking for the work done by friction.
Oh yeah, actually that's true. So I thought maybe we are calculating friction. So if we're calculating just the work done by it, we don't have to expand it. Yeah, that's a good one. So I can just write W friction, say the work done by friction. Who can tell me, do we expect a positive answer or a negative answer for the work done by friction?
Negative.
Okay, reason for that?
Because friction acts in the opposite direction of motion.
Yeah, friction is always going against our change in x or our motion. So we expect a negative answer. If we get a positive answer, we have to ask questions. Maybe we made a mistake somewhere. Okay, let's do the substitutions now. So work done by friction is what we are looking for. The mass is just 1,8, 9,8 for our G. Height at B is on the ground, so 0 minus 1,8, 9,8. At A, we see that the height is 1,5 plus half of 1,8, and then the velocity at point B, 4, right? Minus 1/2, don't forget the squared, 1,8, and the velocity at point A is going to be 0,95 squared. So that will be there. So it's just a straightforward equation. We can just calculate that with our calculators. It'll tell me what you get.
I got negative 12.87.
Okay. Yeah, also I get that. If you get a different answer, just check if you made a mistake or not. So negative 12,87, the unit is joules. So people still forget to write the units, but just make sure you remember, guys, you don't want to lose a mark for that. So the way they would mark this, you already by now know the work done. I mean, the gravitational potential energy at point A, which is this one here. So you're not gonna get a mark for that, but you will get a mark for any of your equation here, and then you're going to get a mark for the final answer, obviously, and then each of these terms. No, actually, because it's 4 marks, I guess the 0 term they won't mark it, but that's what you expect. Okay, any question on this one?
No.
Okay. Someone may ask, if the answer is negative like this, do I have to change it and then say maybe up the ramp or change direction? What would you say to that question?
Are we not supposed to say that and because work is a scalar, so you have to say the work done by is 12.87.
Okay, say that again.
I said work is a scalar, so it cannot have direction. So
Yes.
there always has to be a positive answer, does it not?
Okay, actually the scalar part is correct. So work is a scalar, and yeah, when we have a scalar, it's actually the time where we don't change the negative. A scalar can be positive or it can be negative. It's any number actually. Okay. Yeah. When it's a vector, now you change your negative and make it a positive to say now it's gonna be in the opposite direction or whatever, depending on what vector you're working with. So a scalar, you just leave it as it is. Okay. So that question could have, I think maybe it could have saved someone from a mistake in the exam. So that's what we are looking for actually in these sessions. Make sure those little things that you are a little bit not certain about, get them addressed. Okay, surface BC in the diagram is frictionless. What is the value of the net work done on the object as it slides from B to C? For 1 mark. What do we think? So the question asks for the net work done on the object. You have to get it wrong in order to learn. So don't be afraid to to say your mind?
I want to say it's 0.
Okay, why is that?
Because if there's no friction from B to C, then the only forces act on the block would be Fn and Fg. And at that point, because it will be cos 90, so then it will be 0.
Yeah, that's a good answer. So you can see at this point, there's no more frictional force. So we have no non-conservative forces. I can just say that. So the only free body diagram we can draw is of normal force and Fg. And we see that there's no force that is going in the direction of motion. So the net work done is going to be 0 joules. So that will be your answer. Work net is 0 joules. Okay. If the question was, what is the velocity at point C? What would you say? That could also be for 1 mark. Anyone? Don't be afraid to say what you think.
I think it will still be 4.
Okay. It will not go down. Reason being,
I don't know. I actually do. I'm thinking about, because if it's moving, it's moving in the x direction, right? And since there's no force, I'm thinking of Newton's first law.
yeah.
For it, since there's no force acting on it, would it remain in its velocity?
Yeah, that's absolutely true. Well, there's no net force, which means acceleration is 0. So this can only mean the final velocity is equal to the initial velocity. Yeah, that's a good reason.
Yeah.
Another reason we could have said was, if I do, because there's no friction, if I do my conservation of mechanical energy, this is the equation you get for conservation of mechanical energy. Now look,
because there's no friction, it becomes an isolated system.
yes, true. So now you see that there's no change in height, so those terms goes away. The half, we can cancel the half and the m is the same. And then we are only left now with just vi squared is v final squared, where you can also cancel the square. So at this case, it's just looking more like maths. So you can see that the velocity doesn't change. So there's many ways you can reason that. Okay, good. My only concern is I'm only hearing one voice. It looks 1 or 2. I want everyone to speak, guys. Don't be left behind. Only have 2 days before we write for the classes. Okay, that's done for this one. We have many questions on work. We'll look at some as well as we go. But let's just see if anyone else wants to talk about a different question. Any topic?
Can we do the electricity question?
Okay, electric circuits, definitely. So can someone just read the question for us?
In the circuit diagram below, resistor R with a resistance of 5.6 ohm is connected together with a switch, an ammeter, and a high resistance voltmeter to a battery with an unknown internal resistance R. The resistance of the connecting wires and the ammeter may be ignored. The graph below shows the potential difference across the terminals of the battery as a function of time. At time t1, switch S is closed.
Okay, thank you very much. So once again, we have our diagram. We write everything that's given. R is not known, the small r, but the big R is known. So also we have a switch which is closed at T1. So before that, it is open. Okay. Going to the questions. Define EMF of a battery. These are your questions definitions. We talked about it, I think, during our last session.
Isn't it the maximum energy provided by a battery per coulomb charge passing through it?
Yep, exactly. So you're going to mention maximum energy, or you can say work done by a battery per coulomb or per unit charge. So per coulomb passing through it. So yeah, there we go. This is coming from the equation that says voltage is work over charge. So work over charge, or energy over coulombs. If maybe you happen to forget it, but I don't hope anyone forget definitions. Okay, question 8.2, write down the value of the EMF of the battery. So we look at the diagram that we are given here. Can Mahabo, if you can you explain the diagram, what it means, the whole thing, the one I've circled? Just briefly, what it tells you and what it says about the circuit. I'm not sure if she can hear me. Maybe not. Okay, Shalom, do you want to take this one?
Well, from what I can see, the graph is potential difference versus time.
Yes.
So it's showing the change in potential difference in the circuit, like as time goes on.
Yes. Yeah. And then that's just, I don't know, that's the start. What about the information itself, the numbers?
So from what I can understand, the graph starts at 13 volts. So I think we can assume that to be our EMF. And then it moves down to 10.5 volts at T1. And that's because the switch is closed. So that is...
Okay, I think you cut out at the end there, but yeah, I get your point. So I don't know if maybe Chedza, you have something to say about it before I explain?
No.
Okay. So the graph, basically, it's the potential difference versus time of the whole circuit, or...
Wait, I know.
Yeah.
I know. But as we were talking about the graph, right? Yeah, it's a versus time graph, and the y-intercept of the graph represents the EMF. Because as you can see over time, when it gets to T1, the potential difference decreases. meaning that at T1, that's where the switch was closed, meaning that at T1, that's where the current started flowing, and so there were lost volts due to the internal resistance of the cell.
Yes, that's also good. So we see that before, during this time, the switch is open because they tell us that it is only closed after T1. What do we know when the switch is open? We know that current is not flowing. Current is not flowing. When current is not flowing, we can see that whatever we measure with this voltmeter across the battery is going to give us the maximum work done per unit charge, which is the EMF of the battery. So immediately we can tell that the EMF is going to be 13 volts. And then when the switch is now open at T1, we see that the voltmeter, the same voltmeter, now records 10,5. What happened? This is because the current is flowing, so the internal resistance is using some voltage, which we call V internal or V lost. So there's some voltage lost inside the internal resistance, and that voltage has a magnitude of 13 minus 10,5, which I think is going to come down to like 2.5. And now what we are reading is actually our external voltage, V external, which is now 10,5 volts. So that's exactly what I wanted to hear from you guys. So you just break down the whole question before you even go to the questions. You know, that's a good practice. Okay. 8.2 was to write the EMF. We already know that. So we just have to write it for 2 marks, which is, no, 1 mark. I thought it was generous. So it's 13 volts. 8.3.1. When switch S is closed, now we're talking about the whole circuit, which looks pretty simple to me. When switch S is closed, calculate resistance, the current through resistor R. How do we do that one? So what I like to do is to draw a sketch, a little bit sketch for myself. I represent resistor R here, which has a magnitude of 5.6 ohm. So I'm gonna write everything that I know about this resistor. It's the only one in the circuit, which means the voltage across it is how much? What will be the voltage inside that resistor? Everyone has gone quiet. The question is, what is the voltage inside the resistor R?
Is it not 10.5?
Yeah, at this point, I'm expecting you guys to be pretty 100% sure. In the past, since we started with the class, I'm guessing, is it because, yeah, those words are killing me inside. Because I think you should know this by now. But yeah, that's fine. Just be sure, So that's going to be 10.5 volts because it's the only resistor in the external circuit, and the V external is 10.5. Okay. If we only had the EMF and not the V external, then we don't know what the voltage is because there's also the internal resistance. But because we already subtracted the lost volts, now we know that all the voltage that is left is going inside R. Okay. So now with that sketch, then I can find my current. Just using our good old Ohm's law. So it's that 10.5 over 5.6. I think it's going to be what? 1.88 amps. So how they'll mark that? Your equation, your substitution, your final answer. Okay, looks to be a little bit straightforward. I don't know if the graph could have maybe thrown some people off, but that's what we have. And then 8.3.2 says, what is the power dissipated in this resistor R? So once again, we are dealing with R. So all the given data is there. I can also write my current 1.88 amps. It looks like I have everything I need. It's even more information than I need. So I can use
all three formulas can.
I can use any equation. It looks like this the easier one is this one. So I'll just go with that one. So I get my voltage 10.5, my current 1.88. It might also be a good idea to use power equal to V squared over R. Can someone tell me why I say it's a good idea to use this one?
Because these are values that we're given, not values that we calculate.
Yes, just to be safe, because you could have made a mistake here when you calculated current, but you'll get what we call positive marking, which is good, but to be safe, you just go with the given data. Okay. Then we get 19.74. What is the units for power?
I got 19.69 when I used the V squared over R.
Okay, so this is where they'll accept both answers. Because it could be because we rounded here, which is why we get different answer. So what will be the units? Watt. So they're going to give all this for the markers, people who are marking your scripts, they're going to give them all these options. Any option you can think of using, it's going to be there, and some options are going to have a slightly different answer or even a widely different answer. But if
I've seen on the memos of some past papers there's like 12 options for just one question.
especially for vertical projectile motion, because there's a lot you can do. So you have to know that as well, so you are safe to use any, and if the answer is slightly different, that's okay. Then 8.3.3, what is the internal resistance of the battery?
We can use R is equals to V over I.
R is equals to V over I. Okay?
Yeah, because we know the lost volt. Because the lost volt will be 13 minus 10.5. So then our volt will be 2.5. And then our current will be the 1.8 that we calculated.
That's true, because if I draw my little sketch here. Here's my R. I know that the voltage across it is V lost, okay? It's V lost or V internal, which is 2.5. And what's nice about internal voltage is, internal resistance, it gets the total current, as you can see with my highlighter. So the current coming in is 1.88. You can definitely use that equation. And then your answer.
We can also use the EMF one.
True. So you get this, or if you went with the EMF one, that's what it says. You have everything that you need. 1.88, external is 5.6, internal is unknown. Then you are expected to get the same answer. Even if it is slightly different, let's actually see what we get.
1.31.
1,31. Okay, so you can see there's a bit of, once again, a rounding error, but it's going to be accepted.
Yes.
Okay, how they mark: equation, substitution, final answer. Equation, substitution, final answer. Okay, any question so far? Okay, I take it there's no question on this one.
No.
Then we move on to 8.4. Two identical resistors, each with X, are now connected in the same circuit. So when they tell you it's the same circuit, what can you label on that already?
The EMF, the internal resistance, the current on the ammeter,
Okay, the EMF, the
and
internal
the external
resistance.
voltage.
Okay, let's think about V external and total current. Are these going to be the same if we introduce new resistors?
No.
Yeah.
But then V internal is gonna be the same.
But then V, say that again.
So since EMF is V internal plus V external, won't V internal stay the same?
So because EMF is V internal plus V external, wouldn't this one stay the same? Okay, now the question
I know
is,
the V internal,
yes?
because EMF is always constant, and then the V internal, since it's the same internal resistance, won't it also stay the same?
Okay, that's a good one. It's a good question to ask. Remember,
Can I? Oh,
yes?
what exactly is V internal? Because I think part of the reasons why I struggle with electric circuits so much is because there's like a lot of things to remember. So I want to know what exactly V internal is.
Okay, let's talk about that. That's what I want to hear. Internal resistance. Your battery, the one you use in your phone, the one you purchase from the shop, is going to look like this. You connect it to a circuit where maybe you want to power a table lamp for you to study. So you're gonna plug it like that. So our lamp is going to act as a resistor. Your battery, if you actually, from the shop, before you connect it to anything, if you actually measure the voltage of that, let's say it is labeled, I think most of them are 1.5 volts. It's labeled 1.5 volts. We say, before you even connect it to anything, right? We say that is the EMF, that is the total voltage that the battery can deliver. But the thing is, we never do experiments, but if you do experiment on this, once you connect it to a resistor or to anything, and you measure that voltage again, you're no longer going to get 1,5. You're going to get something like 1,2 volts. So we say, but since I'm measuring the same place, what happened to 0,3 volts? What happened to that? This is where we now talk of internal resistance. So we zoom into the battery and we figure out, oh, inside the battery there's actually the cells and a little resistor in there. So that resistor itself is connected in series, which is very important. It's connected in series with the rest of the circuit, with the external circuit. So it's connected in series with the external circuit. What do we know about voltage? What do we know about voltage when resistors are in series? Is it the same or is it different?
It's different.
Yeah, we say voltage is divided. So the internal resistance is going to steal some voltage, which is why we lose voltage before we even go to the external circuit. So this is what we define as the V internal, or voltage lost inside the battery. So if I actually, this is impossible, but theoretically, if I actually connect a voltmeter across the internal resistance, I will measure the V lost or the V internal. So what's important to know is that the internal resistance still receives the total current because it is connected in series with the whole circuit. So it still gets the total current. Okay.
And we can calculate the internal resistance using the current in the circuit and the lost volt.
Yes. Because
Okay.
I like to do this, so I figured this is important when I was just teaching the grade 10 learner. If you actually do a sketch like this and then you plug your voltmeter and you think of your current, you can actually see now that this is the total current, this is internal, and this is V lost, which means I can use Ohm's law like this. I equals to V lost over internal resistance. Yes. Okay. So now that we talked about that, I think if you practice more, it start to make sense, because it makes sense when you like do questions, I think. All right, let's go to this one. We're still on the topic of whether the V internal is going to be the same or no when we have new resistors. So let me plug a voltmeter there across the V internal, and let's think about that. The internal resistance gets total current. And what do we know about total current when we introduce new resistance? Is it going to change or is it going to be the same?
It's going to change.
So it's going to change. When it changes, it means that V lost, which is I total times internal resistance, when this one changes, this one is also changing, which means this one has to also change. So if this guy is constant, this guy is changing, this guy has to change as well. Has to counteract the change. Do you agree?
Yeah.
Yeah, so Chedza asked this question. I don't know if now it makes sense that V external and current are both going to change. So what we can label is only internal resistance and EMF.
EMF.
Good. Now they say the ammeter reading increases to 4. The ammeter reading was, if I remember, 1.88 amps. I'll just say initial. Now it is equal to 4. So they say, how would the voltmeter reading change? Is it gonna increase, decrease, or
It
remain
will
the same?
decrease.
Okay, say it will increase.
I said it would decrease.
Okay, it will decrease. All right, give a reason by referring to the V internal.
Because if current is increasing, that means the internal will also increase. Thus, the external will decrease.
Okay. So I want to write this. I don't know if there's a way we can remember this. Revive. Oh, there we go. something like this. So revive maybe can work. So R, I, VI, and VE. R, I, VI, and VE. So when you write this like this, in this case, we don't know what happens to the total resistance, but there's a case where we'll talk about it. But we do know that the current is increasing. So current is increasing. This term, V internal, is given by current and internal resistance. Internal resistance doesn't change, which means the whole term has to increase. When that happens, it means V external has to do the opposite. So it has to decrease. So your reason is basically when current increases, okay, I've already mentioned it, so I won't write it in words. When current increases, internal resistance voltage is going to increase. This is why the external voltage or the reading on the voltmeter is going to decrease. Okay,
Because the internal resistance is using more current.
yes, the internal resistance is now using more current because it gets more, it's using more current, well, because it receives the total current, so the voltage has to increase inside it. So if you can follow this, which I just made up now, you are good to go. We'll see more questions where that's going to be useful. Okay. Calculate resistance X. What's the plan?
First of all, I think we should use the EMF formula to find the total resistance, external resistance. Then after finding the external resistance, then 1 over 2x over 1 over 5,6 should be equals to 1 over the total external resistance.
True. So let's say you are sitting in your desk, you're figuring out, you're like, but what do I do? You're holding your head. In circuits, what you can always do is to write your equations down. If you don't know how to solve a question, just think of how many equations do you have. F is equals to I R plus R. I know this happens a lot, also happens to me, but when you have your equations down, you can figure out what you have and what you can do with it. X is the same, but that's not where to start. I have the EMF, I have the current is given, I have the internal resistance. So I can find the total external resistance, which is the resistance that accounts for all these three. So EMF is I R plus R. 13. Current is 4 now. R is not known. I'll call it R external because it is plus 1,33. You could use 1,31 if that's what you got in the previous question. That's also okay. Then what do we get for our R external? While you're calculating, I'll finish my person here, my confused learner. Is that good?
I got 1.92.
Okay, 1,92. Thank you. See if
That's actually not a bad drawing, yes.
that's not a bad drawing. That's what I'm thinking. I'm saying, I'm impressed, even if someone might not give me credit.
It's not bad.
Thank you. Are we all getting the same answer?
Yeah.
Let me see what I get. Yeah, I'm getting the same, so it's fine. Now that we have total external resistance, this is where you have to think about simplifying your circuit. 5,6 and X are in series, so what can we do about them?
We can add them together, combine them.
We can add them together because series we just add. So now we know that these two, which are in parallel, when we add them in parallel, they should give us this value. So we say 1,92 is given by, I'll call this R1 and R2 for now. So, well, it's two resistors, and at this point I think you know that you can say R1 times R2 over R1 plus R2. But even if you don't do that, you can do your 1 over R1 plus 1 over R2. Still the same thing. But now when I substitute, these are in parallel, so that's fine. So I get 2x times 5,6 over 2x plus 5,6. Obviously, at this point, you just do your maths. No one tells you the method or whatever. Maybe my method is a little bit too much, but I'll just continue and see what I get. 2 times 5.6 is 11,2x. On the bottom, still the same thing. So maybe I want to take everything on the left, under to the other side. It's going to be 2x plus 5,6 multiplied by that. Then my 2 times 1,92 is going to be 3,84x plus 1,92 times 5,6, 752 equal to 11,2x. Taking this to the other side, I get 11,2 minus 3,84, which is 7,36x equal to 10.752. And if I divide, I get 1,46. The units, it's resistance, so it's ohm. Okay, if anyone gets a different answer, just tell me, then we can check.
I got the same answer.
All right. Some of your methods can be quicker than mine. If maybe you use this one, it might be quicker. Or someone might choose to say, okay, I can say 1 over this is equals to, there's many ways you can take this. But as long as you don't make mistakes, I'm good. I'm okay with that. Okay, any question on this particular one?
No.
Nothing. So any general question, maybe it's not asked, but any general question you have on circuits, especially Shalom, because you are the one who recommended we do this one.
Is internal resistance always a constant?
Yes, good question. Internal resistance doesn't change. This one is a constant of a battery, just like EMF.
Okay.
All right. Good question there. Just be careful with V lost. V lost is always going to depend on what resistance you're adding or removing. So V lost is going to change, as well as V external. Okay. Now what else do we do? Oh, I even forgot. Is Mahalo still here? I think you are quiet. If you are, can't see.
She's still here.
She muted. I don't know if she can hear me.
Yeah, she muted.
Can you just unmute Mahabo? Maybe the next question is for you. Which question can we do? I think also because you missed quite a lot of sessions. Make sure, guys, you know everything that's given in this table, how to use it. Make sure you know each and every equation in this formula sheet and how to use it. If you don't know any, just point it out for me so that I can quickly explain it.
If there are no other questions, can we do question 10?
All right, question 10. So let's see. Remember this one. This one is not given in paper 2, but you do remember we used it, right, in electrochemistry. So
Yeah.
that one you have to remember. Also have our RMS things here. Okay, it's fine. Let's go to question 10. Question 10 is on photoelectric effects. Can someone read the statement?
During an experiment, light of different frequencies is radiated onto a silver cathode of a photocell, and the corresponding maximum speed of the ejected photoelectrons are measured. The graph of the energy of the incident photons versus the square of the maximum speed of the ejected photoelectrons is shown below.
Okay, thank you very much. So we have a graph of energy of photons versus maximum speed of photoelectrons. Okay, there we go. This is the square of the maximum speed, not just maximum speed. It's the mistake. Oh, they did write it there. Sorry. Okay, too forward. Okay, what are photoelectrons?
Repeat.
What are photoelectrons?
The electrons that are ejected from a metal surface when you light a photon.
Good. So all you have to know, photoelectric effect. There's only just a few things to know here. You have your metal, which contains electrons inside. You have a photon of light of different wavelengths. I'll do the orange light, then I'll do the blue light, then I'll do the ultraviolet light. Okay, so what we know is that the metal is going to have work function, right, which is given by Planck's constant times the threshold frequency. And for the light, what do we know about the photon is that it's going to have energy, which is given by h multiplied by the frequency of the light, which can also be expanded to h multiplied by c over lambda. You are familiar with that equation, right?
Yes.
And then we also have the electron, which is we can find the energy of, which is kinetic energy, given by half m. This m is the mass of an electron multiplied by the velocity squared, which is the maximum velocity of the electron. Why we always emphasize maximum velocities, because sometimes electrons don't move as fast, but what we can do with this equation is only to find the maximum velocity. And then the equation for photoelectric effect says E equals to work function plus kinetic energy, which you can expand as well. So what's important to remember is this guy is for the electron, this guy is for the metal, and then the other guy is for the photon or light. That's all you have to remember. And then another thing to remember is you can manipulate this equation to give you whatever relationship you have depending on what you're given on your graph. In other words, this is your y-axis, this is your x-axis. So if I manipulate this particular equation so that I have E on the y and V max on the x, what I'm gonna do is I'm gonna keep E as it is, work function I'm gonna keep it as it is, plus this one I'm gonna break it down, and it looks like this is already in the form I want. I can rewrite it like this, and what you see is that energy, which is my y, is Vmx, which is my x. So immediately you can identify the gradient, and you can identify the intercept. Is that fine up to so far? That's just the revision of the theory. Is that fine?
Yes.
Okay. Then we proceed to the questions. 10.1 is to define photoelectric effect. What can we say? If anyone can remember it.
It's the process in which electrons are ejected from a metal surface when a light of sufficient frequency is incident on it.
Yeah, good. It's perfect as we want it. Use the graph.
Okay, the code will end in 15 minutes, by the way.
Okay, thank you. Use the graph to answer the following questions. 10.2, write down the value of the work function of silver. Just by
7.48 times to the power negative 19.
Very good. So it's easy to miss this. So remember what we said about manipulating the equation, which you always do whenever you're given a graph. The intercept is the work function. So we can proudly say the work function is 7.48, and then the multiplier multiplied by 10 to the power negative 19 joules. I'll go and check if they'll forgive you for not including the multiplier, but I think they will not, because the answer will be wrong. Okay, so use a relevant equation to justify it. Okay, they also want you to give that equation that we just derived. Well, it looks like this, half m, and then I'll do a dot and write my v squared max plus work function. Okay, then you can say to them, I know that this is equal to this, to show that you know your things. Okay. 10.2, I mean point 3. Which physical quantity can be determined from the gradient of the graph? Just for 1 mark.
Half mass.
What can we get?
Half mass.
Or half mass. So that's a correct answer if they say what is the gradient represent, but they want just the physical thing.
So it's just the mass.
Good. So we can find the mass of photoelectrons. Nice. 10.4. Calculate the value of x on the graph. What can we do? What's the plan?
E is equals to work function plus EK. Then our E would be the 11.98 times 10 to the power negative 19. Then our work function would be 7.48 times 10 to the power negative 19. Then our EK is half mass times velocity squared. And the velocity squared would be x squared.
Right. So we're basically calculating v squared max.
But then what would be our mass? Do we need to calculate it from the gradient?
Yeah, I would say you can do that, but just remember again that it's constant. So you are okay to just go and take it from the information. Right. So that's going to be 9.11 times 10 to the power negative 31.
Where did you get the mass?
Where did I get the mass?
Yes.
Oh, remember it's the mass of electron. And does the mass of an electron actually change?
Oh.
Yeah. Doesn't change. It's a constant. So that's from the information info sheet. Okay, now we only have one unknown.
So then if we have mass, can't we also just find x using the gradient?
Yeah, that's true. You can also just use the gradient to find your missing x. So your coordinates will be that one I marked and this one. Yeah, definitely. So what's the answer we get using this equation? Are you still with us, Shalom? I think you are quiet.
No, I'm still with you.
All right, good. You tell me the answer you get. Okay, I've already calculated. I get 9.88 times 10 to the power 11. So that's my v squared max. But they are only looking for x. So what is my x? What I'm trying to say is that x is
It would be
already
0.988 times 10 to the power 12, so x would be 0.988.
very good. So 0.988, just move the decimal over, then we get times 10 to the power 12, which is the factor here. So our x is just this value. Very nice.
Can we explain how we got the x?
Okay, do you understand this part here?
Yes.
Okay, so we get this equation doesn't know what graph we have. So what we can only get from this equation is our v squared max. The reason why we want to keep it as v squared max is because our x on the graph is v squared max. And another thing is that it's already factored out as times 10 to the power 12. So if I say x is this value, that's not correct. I have to remove times 10 to the power 12. So in other words, I have to take 9.88 times 10 to the power 11 and divide by times 10 to the power 12. Then that gives me the value of x, which will be in terms of times 10 to the power 12. I don't know if that makes sense. Yeah, so if you take 9.88 times 10 to the power 11 and divide by 10 to the power 12, you get what we got there.
Okay, I see.
Yeah, good question. And then we move. That was 5 marks, so they'll give you a mark for any of your equation here. They'll give you a mark for this side as they always do, so both sides. They'll give you a mark for the final answer, and I think the other mark will not be for this, maybe it will be for that, or no, maybe for that, I guess, or 2 marks for that. Anything there, anything that they think is calculated or whatever. Okay, 10.5, the statement on top says the experiment above is repeated using a light of higher intensity. So already you know what they are going to ask when you hear that. So they say, how will each of the following be affected? Choose increase, decrease, or remain the same without any reason. The gradient on the graph.
Won't it remain the same?
Okay, if I ask the reason, what did you say?
Well, since they told us that the intensity is increased, but the gradient of the graph is the mass, so I don't think that's affected.
Yeah, the gradient only gives us a fraction of the, it only gives us a constant, which is half is a constant, mass is a constant. So this is independent of the intensity or any changes whatsoever. So that's very good, that's correct. The number of photoelectrons emitted per unit time.
I think increases.
Increase, okay, reason?
Because intensity affects the number of electrons that are emitted. So since we have light of high intensity, more photoelectrons will be emitted.
Okay, let's quickly review intensity. That's good for those who might have forgotten. Here's a half of our, I guess I'll just draw the whole thing, current reading, and whatever is there, battery. So that's our photo cell. When we have light, it's gonna release photons. If the light is dim, we have less photons. If the light is bright or high intensity, then we have many photons. which means now our photons are going to look like this. We get many photons. And what we know about photoelectric effect is that if the frequency is always high enough, one photon is equal to one electron. So the more the photons, the more the electrons. That's why we say increases. So if they wanted a reason, you're going to say, I won't write it in words again, but photons increasing means that electrons have to increase. Sometimes they mention current, also current increase. Okay, is that good enough? Any question?
Normally in questions like these, they tell us about the cathode.
Yes.
Like in this question, for example, we're told that light of different frequencies is radiated on a silver cathode. Why is it never an anode? Like, what's the importance of the cathode in the photoelectric effect?
Okay, can you check what time we have left?
2 minutes.
2 minutes, okay. I think that will be enough for explaining this part. Well, we are used to anode and cathode in electrochemistry.
Yeah.
But all I can say, I don't want to go into much detail. All I can say is that the one that is receiving light, the metal piece that is receiving light, is always the cathode. So we're always going to define it as the cathode. It's not going to change. Okay. So the one that is receiving light is the cathode. The one that is receiving electrons is the anode. I don't know how important this is in terms of what it does, but it's only the definition so that we can refer to one piece as the cathode and another as the anode.
Okay.
Yeah. So we started a bit late. I don't know if this is enough or you guys want us to do another 10-15 minutes. If you can quickly answer before the time runs out.
I think so far all my questions have been answered.
Okay, anyone else who's not there yet? Maybe you still have a question. Obviously, we're not done with paper 1 because we're still going to have a session tomorrow. So more questions are going to pop out.